Alright, in this video we're going to do another algorithm, and in this case binary search. We're going to start with, let's see, we'll do linear search and binary search. So we'll start with looking at the example on tutorials point. So the problem here is you have a list of numbers that's not necessarily in any particular order, and you have some other number that you want to find whether it's in there or not. So they're looking for 33, and they're giving a demo here of the linear search. So the linear search algorithm just okay, so the linear search algorithm just looks at one item at a time in the array to see if it's the one we're looking for. I'll show you again the way that we think about this. So the way we're thinking about doing an algorithm like this is that you can only see one item in the list at a time as the computer. And what is your process going to be? We're looking for 33, so we test the first number, is that 33? No. Second number, is that 33? No. Third number, is that 33? No. And so on. We go all the way through and get to the end. I have the code started for what we're going to do here, and we'll see how that works. Okay, so here's linear search. It checks to make sure that there are at least two numbers given here. And the way we're thinking about this is that first it's going to have a number that you're looking for, and then you have a list of other numbers, and we're supposed to find out, is this 33 in this list of numbers here? Okay, so first we check the arguments, and then this part here, we take x as the first number listed. The rest of the list, this is the same kind of thing that I did in the last video for sorting. So we take the arguments starting at position 3 to the end, so this would be 0, 1, 2, 3. So this is position 3, 4, 5, and so on in this argv. Okay, so list is going to be those items. They are strings, so this line here will convert each of the strings to a number. Alright, and then we just print the list. We're going to call linear search with the list, which is an array, and the number we're looking for. And what I want to do is have the function return either -1 if the number's not there, or if the number is there, where is it in the array? So it would be index 0, 1, 2 in just this part of the array, which is the list. Okay, so the code for this, you could pause and think, what is the code going to look like? You know you need to look at each number in the array. Alright, so the code is going to be a for loop. Let's see, var I is an index, starting at 0, I is less than list.length, I plus plus, and then we say if list bracket I, so that's some particular list item, if it equals x, we return I. Otherwise, at the end, we return -1. So this is it. That is linear search. The code is very simple. For each index in the array, we check to see, is that item equal to x? If it ever is, we return that index. It would be 0, 1, 2, it's so on. If we get down here, what do we know happens? We know that we never returned, because the way return works is the function's done. It doesn't do anything else. So if we happen to get down here, we know that we never returned and we never found x. That would mean the correct thing to do is to output to return -1. So I have this one here ready to go. Let's see what it says. it should find the 33 at position 0, 1, 2, 3, 4, 5, 6. So it printed the list, and there it is at position 6. Now we could change this 33 to, say, 34, and it should now say that it doesn't find it because there is no 34 in the list now. Not in the list. Okay, so this is linear search, just a for loop to look at every item in the array. Let's take some notes on that up in our algorithms section. So there we have our algorithm, we have sorting, and we'll do searching. Given a list of numbers and a number to look for, it is the number in the list, or array, right? So we use arrays in JavaScript. So linear search, look at each item in the array, return yes for the index. If item is the one we're looking for, return no if get through array without finding what we're looking for. Okay, properties of linear search. So one note is doesn't matter if the list is sorted or not, can always use linear search. So that's a good thing. But what about the running time, which will be bad? If we have n numbers, so over here, if we had n numbers, how many basic operations do we do? How many basic steps? If we go over to our code, we can see if the length here is some number n, could be 1,000,000 or 1,000,000,000 or something like that, how many times did we have to run this line? The worst case is it goes all the way through to the end of the array and doesn't find it, or finds it towards the end. So basically the running time is the length of the array. So we would say the running time is roughly n steps. We call that order n. Okay, so if you have 1,000,000, it'll take potentially 1,000,000 steps. If you have 1,000,000,000 things in there, potentially take 1,000,000,000. All right, that's linear search. Maybe you want to pause and make sure you don't want to watch this part of the video again. Okay, so what we really want to talk about, so linear search is pretty basic. What we really want to talk about is binary search, and I'll cut to the punchline. I'll say TBD is what we're going to say here. The running time is going to be roughly log base 2 of n. Put that here, and so n equals 10 to the 9th, that was our example in another video. This is about 30. So this is going to be an algorithm to find a number in the list. Instead of taking 1,000,000,000 steps, it's going to take about 30. So that is awesome. And that's what computer science is. So computer science is we have to write the program, but then we have to have the right algorithm, the right idea that's going to be the fastest. There's a link down below to this running on tutorials point. Let's see, binary search. Okay, so the main thing that we need for binary search to work is the list or array already has to be sorted. These numbers here are already in sorted order, so we want to make a note of that. Here we are under binary search. We'll have a note, bad, we'll say bad-ish, array or list must already be in sorted order. And we'll see what we do. Okay, so if the array is already in sorted order, and we're looking for 31, so they're looking for 31, and let's just look at the first picture. So the idea here is, if it's in sorted order, you look at the middle, and we remember that we're only going to see one item at a time, so we don't actually see the rest of these numbers. If we look at the middle item, so that doesn't mean that it's half as big as the largest item. It means that if they're in sorted order, this is the one that's in the middle location. Okay, so the middle location is right there. There's a 27. If we're looking for 31, what do we know about where we need to look next? Okay, maybe you want to pause and think about it for a second. So what we know is 31 is bigger than 27. And if this list is sorted, we don't have to look at all these. They're all going to be less than 31 because they're all going to be less than 27. So that means we can get rid of half of the list. We don't have to worry about that side of the list anymore. We didn't even have to look at them. We just looked at the middle. So now we're going to go and look at, so we would have 31 is not 27 either, so all we're left with is this part of the list. Okay? And all we've looked at so far is this 27. And we picked that because it was in the middle. Now we have this part left over. We want to look at the middle again. And the middle of that part is, let me give another thing to cover up here. Okay, so the middle of that part is right here. I'll move this up a little bit. Okay, so the list that we have left is these 5 items. The middle location there is 35. And we're looking for 31. So what do we know we need to look at now? Well, we know that everything over here is bigger than 35. And it will also be bigger than 31. So now we know we don't need to worry about any of that stuff. All we have left is these 2 items. And we look at one or the other first, depending on, we can put it into the code, or, yeah, depending on what the code looks like. It won't matter at this point. We look at one or the other of these. So how many different locations did we have to look at? We looked at the 27, we looked at the 35, and then we may have had to look at both of these or one. How many different operations is that? How many different items did we have to look at? It was either 3 or 4, depending on whether we have to look at both of these. Okay, so that's binary search, and let's look at their picture. So they looked at 27, and then they can get rid of the rest of that. You know 31's not going to be in there. Now they look at the halfway point, and then they know that 31 is not going to be on this part, and then they happen to look at 31 next. And that was 3 operations. So let's take notes on what we do here. So binary search, the basic idea is we look, I'll leave that note first. It must be in sorted order, so we look at the middle location, test if the number we're looking for is larger, equal to, or smaller. Either we found it, right? If we happen to be looking for 27 here, then we would have found it the first time we looked at something. So either we found it, or we can cut the list in half that we need to look at, then repeat. Okay, so we look in the middle, either we found it or we can get rid of one half or the other, and we only need to look at one half. So let's look at the running time. So why is this log base 2 of n? So we start with n, and with looking at one item, one step cuts the list in half that we need to look at. We'll say roughly in half. It's actually slightly more than half because we get rid of the middle and the stuff that's lower, so that could be one more than half. Okay, so one step cuts the list in half, so now we have roughly n over 2 items to consider. One more step cuts the list in half again, so roughly n over 2 over 2, so roughly n over 2 items left. Eventually, we only have one item left to look at. Right? We keep cutting it in half, cutting it in half, cutting it in half. Eventually, we only have one item left. So what we want is the number of steps, call it k, is such that we have n over 2 to the k, right? However many times we run this, each time we cut it in half. So we cut it in half, cut it in half, cut it in half. So there's 1/2, I'll do it like this, times 1/2 to the k, all right? So that's how many are left. This right here is how many are left after doing k steps, roughly. Because you cut it in half, cut it in half, cut it in half. And so we have, if we move things around here, we have n is less or equal to 2 to the k. K was the number of steps we needed. And another way to write that is k is roughly log base 2 of n. So log base 2 of n is the number of times you need to cut in half until you get to 1. And like I said, if we start with 1 billion, we cut it in half, it takes about 30 times. And this would be, let's just do it with, as an example, let's do this with n equals 1024. Okay, so let's say that we start cutting this in half. Half of 1024 is 512. Half of that is 256. This would be the size of the list that we have to look at as we narrow in on where the thing is we're looking for. Half of 256 is 128. Half of that is 64. Half of that is 32, 16, 8, 4, 2, and eventually we get down to 1. So how many steps was this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 steps, and it is the case that 10 is log base 2 of 1024. If we started from 1 million, then we would have 20 steps. We'd have 10 steps to get to 1024 roughly, and then another 10 steps. Okay, so that's supposed to be impressive and pretty cool. It's not a complicated idea, but if you have your list of numbers, your array already sorted, then your running time is way better. So let's say the takeaway, if you're going to have lots of lookups, then sort your data, right? Suppose we're going to have millions and millions and billions of lookups. We're Google or something like that and looking up information. If we're going to have lots of lookups, then it would pay off to sort your data, because every time you need to do a lookup, it will be much faster. Note, there are other tricks as well. See data structures and algorithms, which at ISU is CS 201, 202, 458. We'll put 303. These are all the classes that deal with data structures and algorithms. Okay, last thing is I want to show, so this is what we're supposed to know about binary search. Let's make a note under the lecture. Note, we'll say you should be able to, given a list of numbers, show what happens with either binary search or linear search. Also, say what the number of steps would be for each. So if I give you an array with 1,000 things in it, how long does it take? What's the number of steps to do linear search? It's the number of things in the array. If you want to see what this looks like in JavaScript, there is a binary search here. So this is the code. If you're over here, it'll walk through the code as well. This is the pseudo code. So this is an actual code, but it has the basic idea. We have A is a sorted array, N is the size, X is the number we're trying to search for, and then we do inside of here, this should be the cut it in half part. So they have lower bound is 1, upper bound is N. So we know the numbers somewhere between the first and the last in the array. Here they have computed the middle item. So the middle item is starting from the bottom halfway up to the top. So this is the half right here, halfway. So this is the number of spots in the array that we're looking at, and half of that. So this is the midpoint, and if we look at the middle part, either we're going to be less than or greater than or equal to the number. So if we're equal to the number, we're done. If we're less than the number, what should we do? So that would be the case here. We were looking at 35. This is the part of the array that we were looking at. 31 is less than 35. So what did we change? When we started here, this was the low point, position 5. This was the high point, position 9. We know that if the 31's in there, it's somewhere between position 5 and position 9. Now we know it's not, we know it's smaller than 35, so we want to adjust what we're looking at to look like this. We have the same low point, 5, but now we have 6 as the high point. We know now that it's somewhere between 5 and 6. So if our number is smaller than the midpoint, we adjust the high. And you should pause and think through that that is correct and makes sense. So this was the one here. If x is smaller than the midpoint, then the high point gets changed. We take the top half, we don't have to look at the top half. If x is bigger than the middle, then we change the low point. And that was what happened with our first step. This is the middle. Initially we're looking from position 0 to position 9. 31 is bigger than 27. So now we adjust the low part. We know now that x 31 is somewhere between position 5 and position 9. So that's this statement here. In JavaScript, it looks like this. We have our list coming in. There's X. We have our low point starts off at 0. Our high starts off at the largest index, which is the length minus 1. And then we keep looking as long as we have stuff to look at. So if the low point ever gets bigger than the high point, then it must be that we finished, we adjusted. So if we were here, say we were looking for 32 or 30, let's say we were looking for 30 and we didn't find it, it would be in between these two, so we would adjust the high point down, and the low and the high would actually cross over. And so that's this condition here. It's not super important that you understand exactly when that happens. But so as long as we're going to keep going, we have the midpoint is the low plus half of what we're looking at, and the floor is to make sure we have an integer value. So if we took the average of these two, for example, we don't want to look at index 5.5. We look at index 5. So this is the index of the middle part, and this print here is just to print what it looks like. If we found it, we return that index. If X is too big, then we adjust the low. If X was too small, then we adjust the high. So what you want to do is to be able to, let's see, you should be able to, given a list, show what happens with either binary search or linear search. Okay, so for binary search, be able to say what low, mid, and high are as binary search runs. Let's see how we are on time. Okay, so we can do an example of that to close things out. If we run this, this is the example. So this shows what we're looking at. Initially we're looking at everything, and then this is the top half, and then this is the bottom half of that, and then eventually it finds it. We could put in different numbers and see how it changes. What you would want to be able to do is to do it do it on your own, on paper. So let's go over here. So if this is what we were looking for, and say we're looking for 31, so now I would want to say, okay, this is position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I'm going to have low equals 0, high equals 9, mid equals halfway between 0 and 9 is 4.5, but we round down to 4. Okay, and then we have X is bigger than list bracket mid. So now we say what happens. We know that it's going to be in the top half, so we're going to change the low. So now low is 1 bigger than the middle, 5. So now we have low is 5, high is 9, and mid is halfway between 5 and 9 is 7. Okay, now X is smaller than list bracket mid, smaller than 35. What that means is we're going to look on this side, so we're adjusting the high. So the high, instead of being 9, we know it's going to be smaller than 7, so high is 6. Okay, now we have low is 5, high is 6, and mid is halfway between 5 and 6, but we round down, we get 5. And now we have X is equal to list bracket mid. And it's found. Let's see what would happen if we didn't find it. Let's say that we had 30 instead of 31. So we would go all the way the same up till here. 30 is bigger than 27, it's less than 35, and then we're looking at 31 and 33. So we would have x is less than x bracket mid. The midpoint we're calling 5 there because we take the average of 5 and 6 and round down. So if x is less than the middle, we adjust the high. So high is middle minus 1 because we would know it needs to go that way. So now high is 4. So now we have low is 5, high is 4. That's the end. That was my condition, that the high got lower than the low. So that means we didn't find it. Okay, so this is what I want you to be able to do. If I give you a list of numbers, show me what happens with the low, the high, and the midpoint. And that's it for algorithms. We have two examples. Sorting. So with sorting, we have an algorithm that works. It's order n squared. I claim that there are sorting algorithms that are n log n, so you replace one of those n's with a log n, which will be significantly faster. That will be for the next course. If you take CS201, you'll do that. You could, of course, look it up on your own as well. If you want to look one up, you can look up merge sort. Searching, we have two very simple algorithms. One of them you can always use, but it's very slow. That's linear search. The other one, you need to have a sorted list already, but it's pretty fast. And so the name of the game in the next couple classes, at CS201 and 202, would be you become a better programmer and you learn more of this stuff about, okay, these are the basic techniques for solving problems. The end.